Yes, I think we are now recording the screen. All right. So if you go to our page um, under complex numbers here, when I click on that, I've made a tile that says revision for task 2, and under there I've put 2020's test with answers, 2021's test with answers, and 2022's test with answers. And then I'm currently making this Genius topic summary, which is under there, but I'm just going to open it in my Word thing because I'm working on it still. So the topic summary I've gone through the whole syllabus of it and written a question of each thing you should know. Now, some questions require a few pages to fully go, okay, I've got all the things about this. Some are just very easy. Can I define I? So can I define it? If you can't, you click on the link and go and have a look at what does I mean and how can you use it and how can't you use it. And I've put a little thing where you can go back to the lesson we did on it. So that's good. I haven't finished. I've only got up to sort of here, and so I'm putting more and more things in. And today I wanted to go down to something more meaty that you'll come across, and then start back at the beginning if we get through that, and look at some of the easier things. So there was one particular thing I was liking the look of, and this is number 31. So I'm wanting to go and work that out. So I'll just grab that and go, oh, I didn't grab it. Oh, now look what's happened. What happened?
Just Control Z.
Okay. All I wanted was that. I think I caught something with my sleeve. I caught this because can I borrow your diary? Put it underneath there because the stupid cord. All right. Let's go to the furthest link I've done so far. Just get down to the bottom of the page. Put a new thing in. Sorry, this won't take a tick, but we're going to answer this question today. Z minus 5. Well, something like that. We'll answer one like that. I'll just make that a heading. And I'll go back up here to wherever it is. Sorry, this is link 31. Insert a link. And boom. All right. So, all right, now make sure I've got enough pages at the end of there. I don't run out of room like I often do, and we'll answer a question like that. So there's a question, but how about we solve and I'll leave that one for you to think about, but how about we solve something like Z to the 5 equals Z plus 1 to the 5. Very similar idea. A problem we run into, normally we could do the roots of complex numbers, but this one has got Z's on both sides, and we're going to come unstuck if we just let Z equal e to the I theta, because they're going to have it on both sides and we won't be able to get rid of it like we normally might do for a simple one. Like if you were like Z to the 5 equals, I don't know, 3 or something, you could, or 3i or anything like that, you could work that out because you could make Z be cis theta, so that's cis theta to the 5, and this would be e to the whatever to make, and you could go ahead and solve that. And we've done that, and we'll do that when we do roots of complex numbers again when we revise that. But this one we run into trouble. So there's sort of a standard trick that we need to remember to do. And I don't know, I might have shown you this before. Do you recall this at all? No? All right. So the standard trick is to multiply it by 1. So I'm going to do that straight on up. I'm going to say standard trick 1 times z to the 5 equals z plus 1 to the 5. Standard trick. Now, 1, we can write that in terms of Euler's representation, e to the I theta. We can write that. So I'm going to do that now. I'm going to change 1 to e to the I. Now, at first I thought e to the, I'm going to rub this out, but at first I thought e to the I times 0, because that equals 1. True?
Yeah.
But then I thought, what about e to the I times 2 pi? That will go all the way around and land you with an angle of 0. And then what about e to the I times 4 pi? And what about e to minus 2 pi? So I'm like, all right, if I'm going to capture everything about this, it's actually e to the I, it's 0, but then it's a 0, but plus 2k pi, isn't it?
Yes.
Just like we normally do, we add on 2k pi to whatever the angle. But that's the actual way to write 1 in all the possible ways you can write the number 1. All right, so now I can leave z like it is and just do that. So I'm going to put z to the 5 equals z plus 1 to the 5. All right, so what should I do next? Well, what I'm wanting to do is to take the fifth root of something. So maybe I should get all the z-edness onto one side.
Yeah.
So I'm going to say this is e to the I times 2k pi. I don't have to have the 0 written there each time. And make it z plus 1 to the 5 on z to the 5. Is that right? Because then I can take the fifth root of both sides. And in doing so, I've accounted for the various possibilities. See, someone might say, well, why don't you just take the fifth root of both sides at the very first line and just have z equals z plus 1? Does z ever equal z plus 1?
No.
No. So you haven't accounted for all the various possibilities, but by doing this little trick, you've introduced a k into it, which k will take on some different values, and you are able to account for the other possibilities that actually work. So really, this next step is not needed, but I'm writing it. It's z plus 1 on z is all to the 5 then, isn't it?
Yeah.
Yeah. Now I can take the fifth root of both sides of this equation. So I'm going to do that. We know that this would be e to the 2k pi, on 5i, if you took the fifth root, because you're powering up to a fifth. Does that make sense?
Yeah.
And this guy here would just be z plus 1 on z. Are we happy so far? So what I was saying is, like, we had e to the 2k pi I, and we took the fifth root, so we ended up getting that. Okay. Now I'm going to just multiply and go, this is z e to the 2k pi on 5 I equals z plus 1. What I'm wanting to do now is isolate the z, because I've got to solve for z. Wanting to isolate that z out of it. So my first step was to get it out of the fraction. Now I'm going to go get all the z stuff on one side, so I can maybe factorise it out if that works. So I've managed to get all the z stuff onto the left side and then factorise it. Z into e to the 2k pi I on 5 minus 1 equals 1. And then z is equal to 1 over e to the 2k pi on 5i minus 1. Happy so far?
Yes.
All right. Now, that's not solved it, but if we could figure out values of k that worked and sub them in and then do a bit of work, we might be able to get some answers. But I think we now need to rely on another bit of a trick in order to get what we want. And I'm referring back to your knowledge of things like I'm just looking ahead here, it's a minus thing on the bottom. So your knowledge of something like what is e to the x minus e to the minus, or actually, so not just the x, but e to the I theta minus e to the minus I theta. Do you recall that special thing? I mean, you could work it out too.
Well, isn't that the conjugate of that?
Yes.
So you're subtracting conjugate.
Yes.
Which means you get minus 2 of the imaginary part.
Yeah. So it just is 2i sine theta.
Yeah.
If I added them, I'd get 2 cos theta.
Yeah, you get 2 of them, yeah.
And if I subtract them, I get 2i sine theta. The causes disappear and
yeah.
I get, yeah. Is that right? You said minus. You got me scared.
That was just
Would there be a minus?
No.
No? Okay. So that little guy is what I'm going to aim for to deal with this. The other thing that occurs to me here is this e to the 2k pi on 5 is actually e to the just k pi on 5, but being kind of squared, isn't it? Yeah?
Mm-hmm.
So just in my mind, I've got that idea. But it depends how you want to visualise it. But how am I going to turn e to the 2k pi on 5 I minus 1? What am I going to multiply that whole bottom by to get this guy type of thing happening? I'll just keep doing little asterisks while you think. What could I times a squared by just to get a plane job? To get it back down to a plane job, like just a single. Or what could I times a 1 by to get a minus job?
The minus of that.
Okay, but it wouldn't be the minus of...
Like the minus of the power.
Okay, but not the whole 2k, because you want to go 2k pi on 5 minus a k pi on 5 to end up with just e to the k pi on 5.
Yes.
So I'll write it down as a separate step, so I'm writing next to it. So I had this thing here, and I've decided that I'm going to multiply this bottom layer by e to the minus k pi on 5i. I think, I'm just thinking about it. If I have 2k pi on 5, and then I add on minus 2k pi on 5,
yes,
it gets me just k pi on 5. And if I have minus one lot of that, it gets me minus it. Mm-hmm. So that's, but I can't just times the bottom, so I've got to times the top as well. True?
Yeah.
All right. So that will now give me something that I've got some hope of getting a bit of simplification. I've got e to the minus k pi on 5 I on top, and on the bottom I've got e to the k pi on 5 minus I minus e to the minus k pi on 5i. So what can I do about that bottom layer from the orange asterisk box that we know about?
Make it, write it like that.
Yeah. Yep. So z is equal to e to the minus k pi 5i on 2i sine k pi on 5. This is starting to get somewhere. The top line we can probably write in terms of mod arg, polar form instead of Euler's form now, because the bottom line's cranking out sines and coses and things, right? So let's make the top line do something similar. So what's the top line? I'll write Euler's formula for you. E to the I theta equals cos theta plus I sine theta.
Minus k pi 5 plus pi.
Okay, so you're saying it is cos theta, and I'll just write it the long way, but we know that cos of minus something is cos of the thing. But it's cos theta plus I sine theta. So I've done it the long way. You could have in your mind just directly sort of simplify that. And we're still over 2I sine k pi on 5. So let's scroll and give yourself a bit of room here. Because the bottom line has k pi on 5, I'd like the top line to have k pi on 5 as well, not minus. And that's what we were thinking we would have done anyway. Minus I sine k pi on 5 all over 2I sine k pi on 5. Yay! Now, just like with any fraction, if you've got a sum or difference on the numerator, that's fine, you can split the fraction up. If it was on the denominator, you can't.
Yeah.
So I can actually split that up if I feel like it. I can say I've got a cos k pi on 5 on 2I sine k pi on 5 minus an I sine k pi on 5 on 2I sine k pi on 5. Just split it up. And then it's looking like a bit of a cot. Do you reckon? Yeah. The first one? So I'll just write that. That's looking like a half. And then it's a cot k pi on 5. But I'm going to have to deal with this. There's still an I on the bottom, isn't there? I'm going to have to deal with that. But I've split it so it looks a bit nicer. And over here, thankfully, the i's are going to cancel. So we've got a half. A half, yeah, because the signs will cancel. Yeah. So now how do I deal with this I times the top and bottom by I, don't I? So I'm going to write that as a step. You wouldn't need to in an exam, but I'm going to write it as a step explaining what I'm doing. I'm going to times the top and bottom by I. So I'm now getting that z equals half cot k pi on 5. The top has got an I, but the bottom would be minus 1, wouldn't it? I times I.
Yes.
So I'm going to throw a minus out the front, and then I've got minus a half. All right. Now, that's what z is. What I need to do is throw in values of k that are actually going to give me the different answers for z that I'm expecting. But this is an interesting question because at first people might think, I'm going to come back and answer this, but at first when you look at the question, people might think It's a quintic. It's power of 5. There's going to be 5 answers to it. But if you were to expand the left-hand side, you would get z to the 5. You get a whole bunch of stuff, but it'd start with z to the 5, wouldn't it? On the left side of the equal sign. And on the right side, there's a z to the 5. So what happens? So I'll do it. I'll show you one. Z minus 1 to the 5 equals z to the 5. So we're going to have to come back to this in a minute, but we're just going to talk about the solutions. If you have z to the 5 equals z plus 1 to the 5, is that what that's what my question was. I was talking about minus. It doesn't matter. But that's the question we decided to do today. If you expand the right-hand side here, you get z to the 5. I'm using binomial theorem. So it's 5z to the 4, 10z to the 3, 10z to the 2, 5z and 1. That's what that expands to using the binomial theorem. What could you do to simplify that line of working, since there's a z to the 5 on both sides of the equation? If you were in year 10, what would you do to simplify that? Yeah, you just subtract z to the 5 off both sides. So you actually get 0 equals 5z to the 4 plus 10z cubed plus 10z squared plus 5z plus 1. So it's actually a quartic equation. Looks a quintic the way it was presented. It's actually a quartic equation. So how many answers am I thinking I'm going to get? Yeah. So there will be 4 answers. And that's how I know why there's 4 answers. Why? Because when you expand it in that, you can see it's a quartic. All right? So how am I going to figure out the 4 answers? Well, what's this theta thing anyway? What's k pi on 5? What's that angle anyway? Way back at the beginning, we were saying we had 2k pi there. And that's just an angle like theta, isn't it? And how do we normally give our angle thetas?
What do you mean? How do we normally give them?
We normally give them between minus pi and pi. So I'm going to say normally that normally theta is between minus pi and pi. So let's try putting k pi on 5 between minus pi and pi. What does that mean? We get divide by pi. It's got me a bit worried. Minus 5 to 5, that's way too many, isn't it? So some of them are going to double up. I've done something funny here, so I'm just going to ignore that. I'm going to have to go back and think about that. Sorry about that. I reckon they're going to double up. What we do need to do is find 4 unique solutions, right? So let's just go, well, start with 0. We've got minus a half cot, k pi and 5i minus a half, right? Just got to write that down here. Z equals minus a half. Oh, come on. Computer equals my computer's decided to stop working. Minus a half cot, what is it? K pi and 5?
Yeah.
Minus a half. Okay, so let k equal 0. So I've got the circle of death here. Let k equal 0, we get z equals minus a half cot 0 minus a half. Now, what's cot 0? It's not defined, is it? Not defined. So it can't be that one. All right, so I've done that. Let's let k equal 1. So we get z equals minus a half cot pi on 5 minus a half. There's a solution. Let k equal 2. And we get z equals minus a half cot 2 pi on 5 minus a half. Cot pi on 5, cot 2 pi on 5. Different, aren't they?
Mm-hmm.
Yeah. Let k equal 3. We get z equal minus a half cot 3 pi on 5 minus a half. Different again, 3 pi on 5. We're now in the second quadrant, so that's different.
Mm-hmm.
Like when I look at, pi on 5 is, just do 180 on 5 just to get a rough idea. It's about 36 degrees. So there's your pi on 5-ishness. There's your 2 pi on 5 up at 72 degrees. Your 3 pi on 5 is about 108. Your 4 pi on 5 is about 144. So we can put that one in there as well, where k equal 4, we get z equal minus a half cot 4 pi on 5 minus a half. Now I've got 4 solutions that work. So when I go to 5 pi on 5, that's right there. But what is cot of pi? That's cos of pi on sine of pi. It's undefined, so it doesn't work. And then I go around another 36 degrees there, and I do get an answer that works for 6 pi on 5, but cot of will be the same as pi on 5. Yeah, because tan's positive there, that solution will be the same as that solution. And then probably that's why I'm getting 10 solutions that work. When I go to all of these ones here, like the ones I've ticked there for 6 pi on 5, when I go to 7 pi on 5, that's going to correspond with the 2 pi on 5 one, isn't it? Cot of 7 pi on 5, cot 2 pi on 5. And then when I go around to the next one here, that's going to correspond to that one. And of course the last one, that's going to correspond to that one. So I'd be repeating myself for the values if I put them in. So there are 4 unique solutions there.
Mm-hmm.
Minus a half cot pi on 5, minus a half cot 2 pi on 5, minus a half cot 3 pi on 5, minus a half cot 4 pi on 5, and then minus a half. Now hold on, I've made an error. Where should the I be? I've just left the I out of it, but there should be an I, Crank. After the first thing. So I've kind of written it backwards in terms of, you normally do the real part first, don't you? Yeah?
Mm-hmm.
So I'm just going to go down and just rewrite that here to ask you a quick question about this thing. If z is equal to minus a half, and then minus a half cot of, and it could be 1, 2, 3, 4. 1, 2, 3, or 4. Pi on 5, one of those, right?
Mm-hmm.
can you visualise where on the complex plane roughly that could be? And I'm thinking, I can do a diagram here, a quick diagram. There's minus a half. All of the solutions are minus a half. They're minus a half and then something in the y situation. So all of the solutions to this thing are lying somewhere along on this line here. So some of the cots give a positive answer, like cot of pi on 5 and 2 pi on 5 give a positive, and cot of, and that gives a negative. So some of them, a couple of the solutions are going to be up here somewhere, there and there, for example, and then a couple are going to be down here. Yeah?
Yep.
And does that remind you of any theorem that we have? Oh, maybe I should have done them different colours. Well, that one and that one are kind of going together in some way. Does that remind you of some theorem? Yeah, and then that one and that one. So possibly instead of going 3 pi and 4 pi, I could have gone minus and minus, couldn't I?
Yeah.
And then that might have made it look more conjugate and stuff. I've still got right answers, but yeah. But that conjugate, the complex roots appearing in conjugate pairs only works because
there's real coefficients.
Yeah, the original polynomial had real coefficients, and really, even though the original polynomial was a quintic-looking thing, the original polynomial is actually a quartic. All right, so I bring that up because it's a thing I've seen asked in textbooks and a few times, and I think it's a thing worth looking at. Now, having brought that up, I'd like to look at question from 107. Do you have your textbook there? So I'd like to throw that in underneath here. Actually, do I have something about using Euler's formula? Because, oh, this goes with this trick actually. Exercise 107 and which question is it? Use Euler's formula to simplify. Okay, one moment and I'll look up where I was thinking I was supposed to be looking. Sorry, I'll just go back here. And complex numbers is today. There was one time down here that I said we were going to look at a question. This one. Question 1 from exercise 1D from exercise 107. So that's what I want to write down. But I mean, I've got it on the screen here now, so maybe I'll just capture that as the answer, and I'll just have to write the question down. But it's got this trick to it. It's got a trick happening that we're going to have to point out. So let's just go back onto our review, and we'll write the question first. So the question is, simplify. And it's got minus 5 cos pi on 2 plus I sine pi on 2 on root 5 cos 2 pi on 3 plus I sine 2 pi on 3. The question actually wanted you to use Euler's formula to simplify it, right, in the textbook, but that's the question. And I'll just click down here. Can I get there? Can I get there? Can I get down there? Why can't I?
Enter.
It goes underneath it. Can I get down to here? Come upwards? No. Yep. Okay. I can just paste in what we've said here. So the first thing that was done was the minus 5 on the root 5 in that first line of type working. The minus 5 on the root 5 has become minus root 5. That's just something you would do in year 10 when you're working with surds. No problem with that. What's happened with the angles? What's gone on there? Well, when you divide, you subtract the arguments, don't you? Yeah, you still divide the moduli, which we did for the minus root 5, then you subtract the arguments. So, okay, that's nice. The arguments have been subtracted. And it gives you the second line of working where they were minus pi on 6s for the arguments. And because we had to use Euler's formula, we get that third line of working, which says minus root 5 e to the minus pi on 6I. Yep.
Yep.
Problem. I think the question wanted you to get something which does not, you need to have like a positive mod at the beginning if you're going to have a mod. You're going to have minus something.
Yeah.
So we're going to have to sort out how on earth are we going to make this a positive mod. And that's why I've put this here because, I mean, it's kind of obvious, but it's a little bit like the trick we did at the start of this question.
Yes.
So I took the minus 1 and I turned it to e to the I pi. Because e to the I pi is minus 1, isn't it?
Yeah.
That way, you could put the e's together, and when you're multiplying, you know, when you do e to the I pi times e to the minus pi on 6I, when you multiply, then you just add the two. So add them up and I've got 5 pi on 6, and now I've got the final answer with a positive mod at the front. So possibly this question, I might transfer it. It probably should be changing between, I probably should put it as a question of changing from mod arg form to Euler's form, shouldn't I? That's probably where it would fit in the whole thing, rather than after the question we just did. But just watch out for changing numbers to their, like numbers like 1 or minus 1 into e to the I pi or e to the I 0 or e to the I 2k pi, that sort of thing. All right, so I wanted to do that. I might just start at the beginning here. I'm going to run through quickly. You can go back to this and spend more time if you need to, but just start with the easy things, and I'll add to this over the weekend. So obviously you're supposed to know how all the numbers fit together, and the complex number is the overarching, covers everything, and in complex numbers you've got things like I and 3i plus 4 I've got written there and things like that. You have real numbers, which are a subset of the complex numbers. Obviously that's the real number line is cranking along horizontally when it's represented in the complex plane. And the real numbers, you're supposed to know, can be divided up into rational and irrational. The thing about rational numbers is they can be written as a fraction. Irrational can't. Well, not a fraction using like whole numbers. In terms of decimals, people don't often talk about it, but with decimals, a rational decimal, yeah, terminates or repeats, that's right. So that's rational. Irrational were numbers like pi and e and root 2 and so on. After the rational numbers, you've got your integers inside the rational numbers, which is they're positive, negative, or zero whole numbers, aren't they? Not just positive or negative, be careful. And there's a proof we're going to do in this topic about De Moivre's theorem, where you've got to prove it for all integers. You do the induction for the positive integers, you then use the relationship of that 1 on z is z to the minus 1, so you can transfer your knowledge to the negative integers, but you've got to remember 0 as well as a special case. So there's your integers. Whole numbers are just the positive ones plus 0, and then the counting numbers are 1, 2, 3, 4. You do see those signs sometimes. I've never seen the irrational sign P, but I do see Q come up for rational, R for real, complex, Z for integers, which is annoying because we use Z for complex numbers. N for natural numbers comes up in our course. So we do need to know that. I is a number such that I squared is minus 1. Yeah? It is true, we've chosen I to be the square root of minus 1. But if you were to solve I squared is minus 1, you would actually get plus or minus the square root of minus 1. Yeah. And either of those could equally have been chosen. So I like my definition to be I squared is minus 1. But I is a solution to that equation. X squared plus 1 is 0. And minus I, of course, is another solution. We don't want to forget that. Avoid any manipulations using root minus 1, even though we kind of go, yeah, I is the square root of minus 1, and we get away with it, and people are happy with that. Sometimes if you replace I with the square root of minus 1, you can come unstuck because the surd laws work only with positive surds, like values. So I've given an example there where you'd come unstuck. 1 on I is not the same as going, oh, let's go 1 on root minus 1, and now let's simplify that by timesing the top and bottom by root minus 1. Because the top ends up root minus 1, but the bottom, if you go root of minus 1 times root of minus 1, that'd be 1. True? So you end up with I, but 1 on I doesn't equal I. So just be careful, but if you'd just gone, I'm going to use only I when I do my manipulations and fiddling, times the top and bottom by I, it all worked out nicely like it should. 1 on I does equal minus I. So it's just something to be careful of. We write root minus 4 as root for I, or 2I, sorry. Can you solve these for real values but where b squared is less than 4ac? Like, in other words, ones that you never could solve in year 10, can you now solve them? Yes, you can. You could just use the quadratic formula, or you could go ahead and complete the square, go down the quadratic formula. Used to be you got to minus 31 here and you go, can't do any more. But now you just go, that's root 31i, and you've got your answers. So no problem there, you can do that. Can you work out the modulus of a number? I hope so, after all of what we've done. It comes from Pythagoras on the number plane, because any complex number can be represented by a dot, with the across being the real part and the up being the imaginary part. So you just Pythagoras it. That's the size of the vector out to that dot as well from the origin. Take care. Whilst we can find the size of a complex number, the magnitude of it, complex numbers have no order. So I just picked two complex numbers. I called it Z and W. Z is 8 minus 15i, and W is 12 plus 5i. I found their magnitudes, or their sizes. One was 17, one was 13. So I can say the size of Z is bigger than the size of W, no problem. That's true. The mod of Z is bigger than the mod of W, because the mod is just a real number. But I can't say that Z's bigger than W. That's meaningless, because complex numbers have no order. Who's to say which is bigger than which? Can you determine the principal argument of a complex number? given in Cartesian form there. I was just pointing out that argz is an angle, and I just picked a number like minus root 6 minus root 2i. I did shift tan of the y part over the x part, and I ended up with 1 on root 3. Now, if you actually threw that in the calculator, shift tan of 1 on root 3, that would come out as pi on 6, yeah, from the calculator. But I knew, yeah, because it's a negative and negative, I knew it was over there, so it's actually pi plus pi on 6, like 180 plus quadrant. So 7 pi on 6 is my argument. That's what it is. Well, see, that's fine, and you can work with it. You can do all your working with that and everything, but you are absolutely right. The principal argument has got to be an angle between minus pi and pi, but not including minus pi. So the actual answer is minus 5 pi on 6 rather than 7 pi on 6. And we operate using principal arguments wherever possible. But sometimes when you're, you might multiply two complex numbers together, and you know how you add the arguments? It might come to an argument bigger than pi, and you might be doing some working, and that's fine. You can keep working with it, but at the end you've got to bring it back to a number between minus pi and pi. What's Euler's formula? E to the I theta is cos theta plus I sine theta. And that's the God equation. You're not expected to know the God equation. They're not going to ask you in HSC, what's the God equation? That'd just be wrong. But this is pretty amazing because the God equation contains the heroes of maths, e, I, pi, 1 and 0. And knowing that e to the I pi is minus 1 is a pretty important thing. Can you convert between Cartesian polar exponential representations? And this is where I should go get that last thing we did, where we changed minus 1 to e to the I pi and throw it back in here. Remember that proper polar form is cos theta plus I sine theta. So they can give you one that looks like it is, like 3 cos pi and 6 minus 3 sine pi and 6i. That looks like it's in proper mod arg polar form, but it's not because it's a minus there. So you just got to fix it up. That's improper with the tick next to it, if that makes sense. This one's not in proper mod arg form. It's fine, it works as a number to operate with, but if you're asked to put it in proper mod arg form, you'd need to get that 5 pi and 4 back in the correct range, because that's outside of the minus pi to pi. So whilst the original number exists, and you can work with it, you can operate and everything, really if you're going to be giving your answer properly, it should be the bottom one there. That's all I've got up to. And it's nearly time to go, so I think we might finish there. But what you can do is you can go on to where I've put this thing on your revision for task 2, complex numbers, and there's a few things you can do. You can look at the tasks that were for complex numbers in 2020, 2021 and 2022. And you can also go through here if you want and start ticking off things that you're pretty sure you know about. I haven't filled out further down here. And maybe you'll find some things, oh, not sure about that, or I don't know what it means, but I will try and fill this out, but it could be something to look at. I've pointed out at the bottom that we're not doing in this test sketching subsets of the complex plane. So if you ever get asked, if you see a picture and it's got certain bits shaded and you're asked to say what that is, or they ask you to shade arg this is less than arg that, you know that's something we haven't quite done. It's at the end of the chapter as well. So we're not doing that on task 2, and we're not doing the triangle inequality. I will do that as a special thing after this task, right? But when you go back through the past year's tasks, there might be a couple of them, just ignore them. Okay. All right, well, I'll leave you to it. I'm going to go to my next class. You've got some stuff to do there, and I'll fill that out so we can revise more next week. Thank you very much.